It's July 22nd, 1904. In the heart of Gary, Indiana's steelworks, a 300-ton iron crane shudders across its rails, hoisting a cauldron of molten steel, 2 million pounds, burning at 2,800 degrees Fahrenheit, 45 feet above the shop floor. You feel the heat even from below. The air ripples. Trolley wheels hammer overhead, rivets straining. Without warning, something snaps, a groan, then a roar. The load drops. In seconds, incandescent metal floods the floor, swallowing men with nowhere to run. 22 gone, 48 more burned or broken. The Iron Beast was built for progress, but one glitch turns it into a weapon. How did a machine meant to fuel entire cities become the deadliest thing in the mill? And why did anyone stand beneath it at all? A 300-ton ladle, holding 2 million pounds of molten steel at nearly 2,800 degrees, hung 45 feet above the Gary Mill floor. On the day the crane failed, the official record in 1904 CR-03 counted 22 dead and 48 injured. The floor became a scorched wasteland, concrete shattered and blackened where the steel poured out. The crane, designed as the mill's backbone, became the instrument of disaster in seconds. Trust in machines was a necessity, not a choice. Early 1900s Iron and Steel Institute reports are full of numbers. 80-foot booms, 60-foot swing radii, cables thick as a man's wrist. But when the Gary crane collapsed, those statistics became flesh and blood. The board's calculations, published in June 1905, measured the ladle's fall at over 1 million foot-pounds of force. The impact of a small artillery shell, unleashed on a crowded shop floor. There was no warning. The only sign was a groan from the boom, described by one survivor as the whole building taking a breath. The latch, worn by years of heat and vibration, failed. The load shifted. The crane's safety factor, set at 1.5, was never meant for such a surge. Riveted joints, 3/4 of an inch thick, ASTM A7 steel, sheared instantly. Rails buckled, trolley wheels jumped track, and the molten steel crashed down. The Gary report is relentless in its detail. Every casualty is listed. Name, age, position, cause. The heat alone burned men 20 feet away. For those beneath the ladle, there was no escape. The casualty table from in 1904 CR-03 stands as a grim ledger, each line a life ended or forever changed. John E. McDonough, first investigator on the scene, wrote, "The iron had no mercy. It moved like a river, but it burned everything it touched." His words, preserved in the board's annex, capture the aftermath with a clarity that leaves nothing to the imagination. Steel meant for bridges and railways instead erased lives in an instant. Why did so many stand beneath the Iron Beast? The mill's rhythm demanded it. Production never stopped. Every minute brought a new pour, a new rush. The men trusted the crane because they had to. There was no other way to move that much steel, no other way to feed the city's hunger for rails and beams. The cost of progress was measured not just in tons, but in bodies. The Lottle crane dominates the casting bay, an iron bridge spanning wall to wall, built for one purpose: to move staggering weight through a furnace-bright world. Its structure is as straightforward as it is unforgiving. The gantry, fixed rails bolted high above the mill floor, runs the length of the bay. Each rail is riveted steel, every joint a test of time and heat, each seam a silent question mark. On these rails rides the bridge, a lattice of girders and trusses, sometimes stretching 80 feet, fashioned from wrought iron or early structural steel. Engineering drawings from 1888 to 1905 show a patchwork of plates and angles, every piece held by hundreds of hand-driven rivets, each one a potential fault line. Suspended from the bridge, the trolley glides back and forth, its steel wheels as thick as a man's arm. Hanging below, the boom, a braced vertical frame or massive arm, ends in the hook. That hook, a single curved claw of steel, is the last defense between the ladle and the men working below. In some mills, the hook alone weighs more than a ton. Its job: cradle the ladle's trunnions, tilt, and pour. The ladle itself is a fire brick-lined cauldron, holding up to 300 tons of molten steel, glowing at 2,800 degrees Fahrenheit, hot enough to vaporize water, to ignite clothing from 20 feet away. The true hazard is not just the weight, but the heat envelope. Every inch of the crane exposed to the ladle's radiant energy is slowly softened, annealed by cycles of expansion and contraction. Steel expands nearly half an inch per 100 degrees. A boom might grow and shrink by several inches in a single shift, loosening rivets and opening seams. The Iron and Steel Institute's 1905 supplement notes that, after a year, main bridge members could sag by an inch from thermal cycling alone. Material choices were dictated by cost and availability. Early cranes used wrought iron, prone to splitting under repeated stress. By the 1890s, open hearth steel became standard, but even the best ASTM A7 steel struggled against constant heat and vibration. Safety factors were set at 1.5, but that margin shrank with every swing, every shock, every misaligned ladle. In the open hearth mill, the crane never rested. Operators sat in glass-walled cabs, trusting rivets and hope. The iron beast could move more steel in an hour than a foundry crew once managed in a day, but every link, rails, bridge, trolley, boom, hook, rivets was a point of failure, each detail a blueprint for disaster. December 2nd, 1889. Homestead Steelworks, outside Pittsburgh. The open hearth mill thrums with the pulse of industry, hydraulic pumps, the hiss of molten metal, the clang of iron. Overhead, an 8-ton crane, run by water pressure and muscle, hoists a 5-ton ladle filled with steel at 2,800 degrees Fahrenheit. The lift climbs 30 feet, 3 stories above the floor, suspended by ironwork most men trust without question. That morning, 7 workers will not return home. The Iron and Steel Institute's 1890 report is clear. The crane's rated limit was 8 tons, but the ladle, loaded to 5, always seemed to tempt fate. The logic was simple. If it held yesterday, it would hold today. Homestead's production had doubled in 5 years. Carnegie's managers pushed for more pours, faster cycles, heavier loads. Every hour, another ladle swung overhead, men guiding it with practiced hands. No one paused to check the numbers or question the silent strain inside the metal. The focus was on output, not the hidden risks. The accident struck in seconds. A sharp crack like a gunshot split the air. The crane's arm failed, the boom twisting as rivets snapped. 5 tons of molten steel dropped 30 feet, bursting across the shop floor. The heat vaporized boots and clothing in an instant. 7 men died where they stood. Others suffered burns so severe that even Pittsburgh's best doctors could do little. The Institute's summary is blunt. Excessive load during a pour. No mention of fatigue. No calculation for the shock when a swinging ladle suddenly stops. Andrew Carnegie's response, captured in company letters, was to restore production as soon as possible. Loss of life was tragic, but output mattered more. The safety committee checked the hydraulic system, not the crane's design. No one asked about rivets, heat, or the flexing boom. The mindset was static. If the chart said it would hold, that was enough. Homestead's rupture was a warning, ignored as the mill pressed on. March 1983, Sheffield. Inside East Hecla Works, a new 250-ton ladle crane dominated the casting hall, its steel lattice stretching 50 feet above the pits. Every 4 inches along its girders, a rivet held the promise of safety. That day, a ladle filled with 1,600-degree steel rolled overhead. The men below trusted the ironwork because they had no choice. The main girder, 10 by 6 inches in section, carried the load across the span. Calculations from the factory inspector's report showed the steel faced 180 megapascal of stress, pushing far past the limits of the material. The first warning came as a low groan, then the sharp snap of rivets shearing in sequence. The boom buckled at mid-span. The ladle crashed down, molten steel flooding the floor. 4 men died, 10 were injured. Their names, recorded in the BSA 1893048 register, remain a stark record of the cost. Investigators from the Institution of Mechanical Engineers zeroed in on the rivet pattern. 4-inch spacing, double the recommended pitch, meant each rivet carried more load than it should. The collapse traced a line along a single row, where heat from the ladle had already softened the steel and expanded the girder by nearly an inch. No one had accounted for the combined effects of thermal expansion and dynamic loading. Fatigue, the slow weakening from repeated stress, went unmentioned. The design shortcut, wider rivet spacing to save time and money, left the structure exposed to failure. Sir William G. Armstrong, whose firm supplied cranes across Britain, wrote in his diary, "We build ever larger, but the calculations remain as before. The men below trust not in the numbers, but in the habit of survival." The British Steel Association's 1983 register listed the Hadfield collapse as a warning. Yet, as the decade continued, cranes grew bigger, rivet patterns only slightly improved, and the lessons remained incomplete. The physics of rupture, how heat, stress, and time conspire, were still poorly understood. The risks, hidden in the seams, continued to grow. A ladle crane in motion carries more than just weight. It holds raw energy, coiled and invisible, waiting to be unleashed. When a 300-ton ladle moves at just 4.5 meters per second, a brisk walking pace, the numbers become staggering. The kinetic energy that builds inside the steel, the rails, and the cables is not a theoretical hazard. It's a real, measurable force. The 1905 issue of American Machinist laid out the formula, simple and chilling. Kinetic energy equals 1/2 the mass times the velocity squared. For a 272,000 kilogram ladle, 300 tons, swinging at 4.5 meters per second, the result is 2.9 million joules. That's more energy than you'd find in 700 kilograms of TNT. In plain terms, the Iron Beast becomes a moving bomb. Its destructive power determined not just by gravity, but by speed. But the physics doesn't stop with movement. Heat seeps into every bolt and beam. Steel expands when it's hot. The thermal expansion coefficient for structural steel is about 12 millionths per degree Celsius. Multiply that by a temperature swing of 1,500 degrees from the ambient air to the searing heat near the ladle, and a single 80-foot boom can stretch by more than an inch, 30 millimeters, enough to open seams, loosen rivets, and shift the geometry of the entire crane. The expansion is slow, but relentless. Every cycle, every pour, the structure grows and contracts. Over time, these tiny shifts become gaps, and those gaps become cracks. No static calculation can capture this creeping threat. What does it mean for a crane to carry the energy of a battlefield shell, or to grow and shrink with every shift? It means that safety factors, set by engineers in quiet offices, become meaningless in the heat of the mill. The Iron Beast is never truly at rest. Its mass, its heat, and its velocity create a system always on the edge of control. The men below might trust the numbers, but the numbers are only as good as the last calculation. When a latch fails or a rivet slips, the unleashed energy is instant and absolute. The ladle doesn't just fall, it detonates, pouring steel and shock through everything in its path. The physics is unforgiving. The only question is when the next calculation will fall short. Across 3 decades and 2 continents, the same pattern repeated itself. No matter the country, no matter the size of the mill, the ladle crane was both the pride of the works and its most unpredictable threat. Reports from the Iron and Steel Institute, the British Factory Inspectorate, and the Indiana State Board all describe the same sequence. A boom, already weakened by years of heat and vibration, gives a warning groan. Rivets, spaced too far apart or fatigued by 1,000 cycles, snap in rapid succession. The load shifts, the structure fails. Molten steel, always at the edge of control, finds the smallest opening and pours through it. Each investigation tried to explain the collapse as an isolated failure, a faulty latch, a misjudged load, a worn cable. But the records reveal something deeper, a mindset that treated each crane as a static structure, its limits defined by yesterday's calculations and the hope that nothing would go wrong today. This is risk normalization, the slow, invisible process by which extraordinary danger becomes routine. The Homestead rupture, the Sheffield collapse, the Gary disaster, each one different, yet all shaped by the same blind faith in numbers and habit. The Iron Beast didn't just fail once. It failed in the same way, again and again, because the system accepted risk as the price of progress. Official inquiries into crane failures often missed what now seems obvious. After the Gary disaster, the Indiana State Board of Inquiry combed through every rivet and calculation, yet their report closed with a single damning phrase: no evidence of fatigue. Investigators pored over the broken boom, measured the sheared rivets, but dismissed the possibility that years of heat and vibration could slowly weaken steel. The board's calculations, published in 1904 CR03, focused on static loads and the final, catastrophic moment, never the millions of cycles that came before. In the annex, John E. McDonough's field notes mentioned faint lines near the fracture, but his observation was buried, never discussed in the main findings. The Royal Commission on British Steel Plant Safety, reporting in 1912, ran fatigue tests on similar riveted joints. Their results were clear. At 150 megapascals, failure could occur after 1 million cycles, well within the working life of a crane in a busy mill. Yet the Gary board dismissed fatigue as a theoretical concern, not a real-world threat. The absence of formal standards left engineers to trust their instincts, and the official record closed the door on a line of inquiry that could have saved lives. Only later would these missed warnings justify the push for mandatory fatigue inspections and stricter codes, but for those working beneath the Iron Beast, the danger remained unspoken, hidden in the seams. Regulation came not as a single breakthrough, but as a series of mandates forged in the aftermath of catastrophe. In 1915, the American Society of Mechanical Engineers met in New York, their minutes echoing the failures at Homestead and Gary. They set a dynamic load factor of 2.0 for ladle cranes. No longer would static calculations protect workers from the force of swinging steel. Every crane over 150 tons now required mandatory fatigue inspections, forcing engineers to search for cracks before disaster struck. Meanwhile, Britain's 1918 Factory Act Amendment responded to the collapse at Sheffield. Lawmakers wrote in mandatory rivet testing and required a half-inch clearance for every 100 degrees of heat, recognizing that steel expands and molten metal reshapes its container. Hansard debates from that year reveal Parliament's urgency, haunted by lives lost to overlooked seams. For the first time, law treated the Iron Beast as a threat, demanding vigilance and rules written in steel. Today, steel still flows overhead, now guided by digital sensors and redundant safety systems, not just rivets and human instinct. Yet every time 1,000 tons hang above a shop floor, the old equation returns. Ambition versus risk, precision against gravity. The Iron Beast may have changed its shape, but the stakes, measured in lives and molten metal, remain as real as ever. Share your thoughts below.